So we have a bunch of things going on, at least that I'm involved in the next, and it's kind of, a lot of them are starting up soon. One of them is, of course, the one we're in right now. That's already started. Coming up, we're going to do like a special little mini course, a little mini review of Jeremy's, and well, Terence Parr and Jeremy Howard wrote this paper on the matrix calculus you need for deep learning. It's a really nice little paper. It's about maybe 28 pages or something like that, but it's very compact and really gets to the meat of the matrix differentiation techniques that's really most of what we're ever going to need for understanding neural networks. And so I'm going to do a little mini review of that over the next 2 Sundays at 8 a.m. Pacific time. That is tomorrow and next Sunday at 8 a.m. Pacific time. I've peppered the whole, yeah, I've peppered the Slack group with advertisements for this, so you probably have seen it already. But anyway, if you're interested, I think this will be a really nice way to spend your Sunday morning. I plan to go through half the paper tomorrow morning and the other half on next week. And the way we're going to do it is, I don't want you to have to do any homework. You're just going to show up. You're going to dedicate the next, from 8 to 9:15 to reading, and then the next 45 minutes we'll discuss what we read. So it's kind of a no-brainer way. You just sort of schedule that time slot, for, those 2 hours tomorrow and the 2 hours next Sunday. And in those 4 hours, we're going to learn everything we need to know about matrix mathematics that are needed for neural networks. I think that's a pretty good deal. The only problem that I foresee is you need to have at least a rudimentary understanding of calculus already. I mean, we're not going to actually teach you calculus from the ground up. We're going to assume that you've had that basic first-year calculus that you know, and it doesn't even take a whole year to. Basically, you have to know what differentiation is, and we'll introduce the chain rule, but you basically have to know what a derivative is. That's really the prerequisite for the class that I didn't state. So sorry about that. Yeah.
Joseph?
Yes, sir.
We have the part 1 class at 8, right?
Which class?
Learning. The Fast AI Deep Learning part 1 class at 8, right?
Oh, I'm sorry. It's not 8 o'clock. It's 10 o'clock.
Okay.
Sorry. Yeah. Let me make sure of that. Let me make sure that did the announcement that I put on Slack say 10 o'clock?
It says 10 there, yeah.
Okay, good. So I didn't get confused then, but I'm confused now. So thanks for unconfusing it. It is 10 o'clock tomorrow and 10 o'clock next Sunday, and those times are Pacific time, okay? All right, so that's one thing. Then that class is going to, that little review, that time slot is, after the review is done, the following week, we're going to start, people that are interested will start this hands-on machine learning class, which I also wrote an advertisement about that, but here's the schedule for that. And so this is going to be like a really deep dive or long-term class. It's based on this text, Hands-on Machine Learning by Aurélien Geron. I'll see if I can get that, open up the link. Here we go. So this is the textbook. It's the second edition. It cost $44 on Amazon. I hope that won't be a barrier to anybody. If that's a barrier to anybody, please, if you would take the class, but except you couldn't afford the $44 for the textbook, direct message me and we'll figure something out. Anyway, so it's going to be based on this book. This book is an amazing book. I haven't read it, of course, but I've looked at it, and let's just look at the table of contents. This is basically a tour of the state of the art of machine learning as of 2019. And it goes through all the classical machine learning techniques, of course, regression, gradient descent, regularization, logistic regression. These are all non-neural network techniques. Support vector machines, again, a non-neural network technique. So these are the classical machine learning techniques. Decision trees, random forest, ensembling, dimensionality reduction. So there's 8 chapters right there. And then we do unsupervised learning techniques like k-means and clustering, Gaussian mixtures. And then part 2, we don't get to neural networks until part 2. And then we start, going through, going through the artificial neural networks. And in this case, they're using Keras and TensorFlow, which is good. It's good to learn. I mean, we all love FastAI. We all love PyTorch, but in the world of work, a lot of people prefer and use TensorFlow in their toolkits in their corporate environments. So you probably want to become fluent in both PyTorch and TensorFlow, and this course will give you this course will give you an opportunity to do that. Okay, so go through a lot of work in neural networks, getting introduced to TensorFlow, pre-processing data, all the things we've been through in the FastAI. Using the FastAI package. Now we'll learn how to do that in TensorFlow, loading and pre-processing data. Then we have computer vision with CNNs. And then this is something new that we haven't done in the FastAI classes, generative, autoencoders and GANs. I think they touched on autoencoders in the course number 2, in the part 2 of the course, but GANs, these generative adversarial networks is a new topic. And then, of course, reinforcement learning is really gaining, like if you look at the recent conferences on neural networks, reinforcement learning has been getting an increasing fraction of the papers that are being presented there. So that's an important new technique. And then the final one is something dear to Sam Charrington's heart, which is training and deploying models at scale. That's also something we don't touch on in the FastAI classes, but is also really important in industry. So, going through this will give you a really thorough introduction to all the different aspects of machine learning as of 2019, and you'll sort of be close to the state of the art in all these areas. So when you look at it that way, $44 spent on buying this book is one thing, but $44 spent on buying this book and then getting to experience it in the context of a study group, that's really worth a lot more than $44. So to me, it's worthwhile to buy the book. But again, if that's a deal breaker for you, if you can't afford the $44, direct message me and we'll see if we can work something out. Okay, so that's that advertisement. Another course that we're going to start soon is yes, sir.
What will be the format for the reading book? Is it like just the way you made mention about the reading the paper for mathematics for machine learning, 1 hour, 15 minutes, and then, so what's the format for the book?
Yeah, that's a really good question. I haven't determined that yet. So here's the schedule. I wanted to go back to the schedule. We're going to have an orientation meeting first, in which we'll discuss that. We'll try to, I'll think some more about what the format should be, and you guys can give me your ideas, and then we'll get started on June 7th. And it's going to be the same time slot that the mini course review is taking for tomorrow and next Sunday, the 10 o'clock time slot. I thought about the reading thing, just sit there and read for 1 hour and 15 and then discuss for 45 minutes, but that might not be the right way to do this book, because it's more of a hands-on. And so we're probably going to want to demonstrate code and stuff during the lectures. And also be aware that this course is not going to be just something where you show up on Sunday and that's it. You're going to probably be working during the week to implement code and stuff, and work on writing code. So this is going to be a big undertaking. If you do it, make sure that you have a reasonable amount of time available. It's not just going to be the Sunday the 2 hours on Sunday. And it's also a long haul. In order to get through this, I've found that most of the chapters are going to take two weekends to go through. So the shorter chapters we can do in one day, but most of the time we're going to be spending 2 weekends on a chapter. And so, since there are 19 chapters, we're going to be going at this for 32 weeks. And it's going to end in February of 2021. So it's a long haul. It's a long-term project. But I think if you, you know, if you're interested, I think it'll be a very worthwhile project. I've also built in a couple of holidays. We have a 4th of July holiday in this country, so that weekend we're off. We have a Labor Day holiday here. Labor Day holiday here. And we have a Christmas holiday here. So there's three off days, but the rest of the time we're just going at it every Sunday. Okay, so that's that one. And then
Joseph,
yes,
Joseph, can I suggest, it's already 1:15. Can I suggest we get on with the content for today, and then maybe we have the rest of the announcements at the end of the class?
That's reasonable. Let me just do one more announcement because I'm done. I'm almost done. I got like 1 more minute left, but I take your suggestion. We're running out the clock here. So the last announcement is this FastAI library class, version 2 library. We're gonna go through Jeremy's walkthroughs. Jeremy came up with a series of 10 walkthrough videos back in September, I think, and I thought that as an extension for our DL1V4 study group that we had, which we're about to conclude, that will, in that time slot, we'll continue on with this, the 8 o'clock to 9:30 time slot. We're going to be done the next 2 lectures for Sunday, the next 2 Sunday lectures for the Deep Learning 1 version 4 will be done by Gautam, and it'll be on the NLP part. And once we're done with that, we'll move smoothly into this library study group if you're interested. We're basically just going to straight walk through each. We're going to have an orientation meeting, and then we're just going to do 1 video each Sunday, and then so it'll take 10 weeks. So that's the schedule. And by the way, for all of these classes that I talked about, including our class, the library class, the hands-on machine learning class, I invite anyone who's interested to sign up to lead the discussions. You know, I don't necessarily want to lead them all. I want to leverage all the expertise in our community to do that. Okay, so thank you for reminding me, John. I'm done with the announcements. Let's get into the to the class. Okay, I had a little trouble with this is from last week. I had a lot of trouble getting Gensim to work, so I wasn't able to finish assignment 1, but I did look through it. This is basically just a little exercise they did to look at word analogies. So this is really easy. You don't have. I don't think there's anything to write for this one. But you do have to be able to load. This is the part I couldn't do on my computer. And even though many people, Larry and Srinivas, offered some great suggestions, I followed them all, and I still haven't got it to work. So if you want to go offline later on and make, if you see something that maybe I didn't do, let me know. So this is the homework assignment that I had hoped to be able to do by today so we could talk about it, and I didn't do it, but I did look through it. And he's basically taking you through 2 different methods, or 2 different types of methods for getting word vectors. One is count-based word vectors. And this is basically, remember, you take some kind of you build some kind of a Word document matrix that has, let's see, it could be Word document matrix or a word matrix that are based on word counts. So if you had a Word document matrix, you'd have a very long list of rows, because each row would be for one of the words in your dictionary. Your dictionary might have tens of thousands of words in it. And then you'd have columns for maybe documents, or maybe maybe the columns would also be the same list of words. So you'd have this huge n by n matrix, and the entries would be the counts of a given word that relate to a given. Let's see. So the words on the rows would be the center word, and the words on the columns would be the context word. And so the counts would be of a row and a column. The entry in that matrix, well, the matrix entry corresponding to a word in a row and a word in a column would be the number of times that context word has occurred related to that center word. So it's a count, you know, like the number of times that word appeared within a window, a context window of ±5 or ±10 or whatever they decided was the right context. So that's how you build this this count-based word vector. So here it is, like, you know, a list of words. The same list of words are the columns, and then you have a little document. You have a couple of documents, and then you count the words, the number of times that a given word occurs in context with another given word. So let's take this, for example. All is the center word, and is a context word that occurs within ±5, a window of plus or minus whatever it is of all. Okay, so if you look at is, and you look at our documents, all that glitters is not gold. So is does occur within, oh, let's see, are they taking, they didn't specify the size of the context window here. To me, oh yeah, all
The window
in the
is one,
context
Joseph.
of, the windows aren't defined, but so to me,
It's one.
it should be two though, right?
It's written
Because
on the. It's written right below the paragraph. Co-occurrence with fixed window of n equal to 1.
oh, there it is, window of n
Yeah.
equals 1. Thank you. So if you just take a window of 1, then this is not in the context of all, right? But this instance of is in the context of all. So the entry for all as the center word and is as the context word, the count is 1, right? Everybody see that? That's how you populate this matrix. And this is just a simple case, but you can imagine a much more complicated case. Okay, so then the next step, once you've got this matrix populated, you then do a SVD decomposition of the matrix. SVD is a method of, you can think of it as a black box if you haven't become familiar with this method yet, but what it does is a method of matrix factorization. Given a matrix, you can factorize the matrix into 3 factors, and you can decide how big, how many, so you can decide what the dimension of the embedding should be by deciding by doing this principal components method and just take the top k, where k is the same as the dimension that you want. So in general, this method starts with an n by n matrix, and all of these matrices would be n by n. But if you just want, but usually the principal components method is designed to reduce dimensionality. So you generally want to just take the top k, where k is a much smaller number than n. And in this case, k is going to be the same as the d, the dimensionality of our embeddings. So the idea then is to break up these words, break up this this matrix, factorize it into pieces, and then one of these pieces, I think it turns out to be the u. Actually, you get the u and the v. You get 2 different representations of the word vectors. And remember, in word2vec, they talked about having two different representations, and they really didn't explain why. Well, this sort of is a clue as to why, because there are 2 different embedding matrices that come out of this decomposition, and so they use both of them in word2vec.
I think that's not quite accurate though, because your matrix is symmetric up above. I think this is a general description of SVD, that the SVD is used for asymmetric matrices, and therefore you're getting 2 different orthogonal matrices on both sides. But for the matrix that we just built, we are going to actually, because it's symmetric, both sides will be the same, right? The U and the V. They will be orthogonal to each other.
Oh, okay, that's correct. That's correct. That Murad makes a very good point. This method of SVD is in general method of decomposing matrices that are rectangular, not necessarily square, and that's why it's so useful. And so this is showing that. And so in general, you will get different. The U is an orthogonal matrix, and the V transpose is an orthogonal matrix. The rows are orthogonal to each other. But as Murat said, when you have a square matrix, the U's and the V's will be the same. So, okay, so that doesn't explain why they have two yet. We'll think about that later. It could be that if you take the product of S and V, that's different than U. And so that might be what they use for the V. I'm not sure. Anyway, so that's one technique, is this count-based word vectors. Okay, so another technique is, okay, so they lead you through an exercise of working with count-based embeddings, deriving the embeddings using the SVD, and then doing some interesting exercises with them. You know, you reduce, here's the step where you reduce dimensionality, then you write some kind of a plotting routine, then you plot the word vectors on then you reduce to 2 dimensions and plot them, and plot some of the vectors. And so, okay, so that's the end of that exercise. Then you do the same thing with a prediction-based word vectors. And these prediction-based word vectors are the word2vec and the glove kind of, let's see, I think in this case they're word2vec. And so here we start with the word2vec embeddings instead of deriving the embeddings ourselves. And then we reduce the dimensionality by the same technique, truncated SVD. And then we go through some similar exercises. And here they introduce this distance measure that we've seen before called the cosine similarity. So if you take, so one way, of course, to take the distance between 2 vectors is just to subtract the 2 vectors in space and get that distance, and get the distance as the length of the vector of the difference vector. So, for example, x minus y would be the vector going from y to x. Sorry, yeah, the vector going from y to x. That would be the distance vector in 2-dimensional space, and then the length of that vector would, you could say that you could use that as a distance measure. But instead, they use this. They just use the cosine of the angle between them as the distance measure. That seems to be widely adopted in NLP. And
sorry, I think the reason for that is that the meaning, because of the way that the matrices are calculated, the directions of the vectors are pointing at the meaning. But where along that vector you reside is not as important in terms of the meaning. Therefore, if you're comparing 2 vectors, whether they are analogous in meaning, you look at the angle between the 2 as opposed to Euclidean metric between the 2.
That's an excellent point. So if you took the Euclidean metric, it's just a number. It's just going to be the length of this vector. And as Murat just said, it turns out that, and we'll see this, we've already seen it, that the directionality of these word vectors has a special meaning in this embedded space. So the cosine distance takes that into account, takes that directionality into account. And the part that I haven't understood yet is, as Murat said, the distance along that the vector isn't so meaningful, and I'm not sure why that is. So, but the point is that when we take the cosine, the theta as the distance measure, we're basically throwing away this information that we could get from the length of the vector. But as Murat says, it's not important, and I'd like to keep my mind open and try to understand why that's true. But let's move on. So what is the cosine distance? Well, if you take the dot product between two vectors, you know, you remember this from your high school class, A dot B is the magnitude of A times the magnitude of B times the cosine of theta. So if you take A dot B, or in this case P dot Q, so let me rephrase that. P dot Q, the dot product of P and Q is going to be the magnitude of P times the magnitude of Q times the cosine of the angle between them. You can turn that around and solve for the cosine. The cosine of the angle between two vectors is the dot product of those two vectors divided by the lengths of the product of the length of those two vectors, and the cosine lies in the interval -1 to 1. So this is the formula for cosine theta, and that is called the cosine similarity. Now in NLP as the distance measure, they actually use 1 minus the cosine similarity, because that acts more like a distance. So think about cosine similarity. The most similar you can get is the word to itself, right? The word is most similar to itself, and the cosine of the angle would be 1. And so a value of 1 means the word is basically as similar as you can get, and a value of -1 means the word is as dissimilar as you can get. And this would be useful for looking for antonyms, you know, opposites. But when you, excuse me for a second, let me finish. So when you're talking about distances, you want the word itself to be a distance, the words that are closest to this word to be at very small distances from it. So instead of using the cosine theta as the distance, you use 1 minus cosine theta, and that acts more like a proper distance. The word is at a distance of 0 from itself, and all words that mean nearly the same thing are at very small distances from the word, right? So someone had a comment?
Yeah, I was pointing out that that there were some questions inside of the chat.
Okay, let's deal with those. Yeah, thank you. Let's deal with those. Chat, lots of questions. Okay, if you want, speak up, represent yourself in these questions. That way I won't have to read it. Let's see. Lots of good information about SVDs. If vectors are normalized, it's almost the same. Yeah, if you normalize the vectors, then it's exactly the same. Then the point is that if you normalize the vectors, then the cosine distance is the only thing that encodes any difference between the two vectors. But to normalize the vectors, you're throwing away the length information, and that's the thing that I'm interested in understanding why it doesn't matter, as Murat said. It doesn't matter that you throw away the length information. And someone said it has to do with centering the measurements. Abhijit, do you want to explain that a little bit more detail?
Yeah, what I mean is that when you center the you can calculate the Euclidean distance by taking the raw numbers, but if you center the measurements, make the mean equal to 0, and then do your calculations, then the two things will come out exactly the same. Otherwise, Euclidean distance will differ from the method which is shown here.
Oh, so you're saying subtract the mean, you know, over the entire corpus, basically center everything so that the mean of all the words in the corpus is at 0.
No, if you have two vectors x and y, you have to center x and you have to center y, and then do the calculations.
Yeah, that's what we've done here in this. Am I sharing the right screen? Are you seeing this cosine theta?
Yes.
Okay, so these two are centered, right? X and Y are tail to tail, so they're centered.
Yes.
But
yes.
X and Y could have different lengths, like Y could be out here, you know, but the cosine distance would be the same. In other words, the cosine distance of any word along this line, or any word along this line is going to be the same, right? And that's the information we're throwing away, is the length.
Yeah, so once it is centered, the Euclidean distance will also should come out to be the same.
No, the Euclidean distance is completely different. Completely different than the cosine distance. The Euclidean distance is a number, is a distance. It's like and so it's a positive number from 0 to infinity, or 0 to, the Euclidean distance can go from 0 to infinity, whereas cosine distance can only go from -1 to 1. Okay, then he talks about this.
Yeah, that's right.
Yeah. So, okay, and then he moves on to this polysemous words, and that's the idea that you could have a word that has many different meanings. So like leaves, right? You can say leaves could be a noun. It means the leaves from falling from a tree, or it could be he leaves the classroom tomorrow morning at 10. That's two different meanings. There could be even more meanings. So he talks a little bit about how you would handle that, and he also makes a reference to a whole paper that's written about this. But let me move on. Synonyms and antonyms. Again, synonyms would be words that would have a distance close to 0 from the word. In other words, a cosine distance, 1 minus cosine theta. That's what I mean by cosine distance. Let me see. I'll annotate a little bit. Yeah, here. A pen. Come over here. So you will see this in the future. They talk about cosine similarity here, but what we ultimately use is called cosine distance. This is really inefficient, but okay, cosine distance equals 1 minus cosine theta. So you can see that its range is going to be from 0 to 2, I think. Let's see. Yeah, it can range from 0 to 2, right? Because when the cosine is negative
right.
1, it can be 0. If the cosine is 1, then it can be 0. But it can't be. It's always going to be in that range. So if you're looking for synonyms, you want to find words that have a cosine distance of 0. And if you're looking for antonyms, you want to find words that are as far as possible away, and so they have a cosine distance of 2. Does that make sense to everybody? Because they talk about antonyms and synonyms later on in this homework assignment. Okay. Let's see, back to my mouse cursor. Okay, so next they do that exercise. Then they talk about solving analogies. Analogies are this thing where, man, you've seen this famous thing, man is to king as woman is to what? Woman is to queen. And there's actually a mathematical formula. When you have word vectors, you can actually relate them using word vectors. So let me illustrate this really quickly, and then we'll move on. Okay, so let's say x. I haven't got my pen back yet. Let's see, I want my pen. Nope, it's not giving me my pen.
Joseph, I haven't had a chance to look at the assignment. Do they provide answers also?
I'm not sure.
Okay.
I'm not sure. I'm sure that people have put them online. I don't know. I can't get my pen back. Anyway, there's a mathematical way to represent this. And let's see, back to, I just can't get my pen back. Clear all drawings and then make me another one. Okay, sorry, I'm not going to try to do it. The idea is that man is to king as woman is to what? Let's say woman is to x. Well, the idea is that if you have word vectors in this space, then as Murat said, there's a directional. It turns out that the direction has meaning in this embedded space. So man minus king should equal woman minus queen. Sorry, woman minus x. I sort of gave it away, but man minus king, the word vector for man minus the word vector for king should be equal to the word vector for woman minus the word vector x that we're looking for. So you can actually solve for that x algebraically, and that's what you actually do. And he actually goes through that exercise, and then they have you explore more analogies, and they actually have you just play around and find some analogies that you expect to work, but they don't work. And then they talk about bias by looking at this analogy, woman is to boss as man is to what? man is to boss as woman is to what. And they show you that in language has implicit biases in it, and then they ask you to go and find some more of them. And then they ask you to go and think about why there are biases. So that's kind of a summary of the homework assignment. I had meant to go through the whole thing, but I wasn't able to get it running. So that's that. There are a couple of papers that he refers to. I didn't look at these, but maybe improvements on WordVec, evaluation methods for unsupervised embeddings, latent variable model for PMI. PMI is something like something about information. It's something about entropy. I look. You can look this up, but I didn't go through these papers. Yeah, here it is. Point-wise mutual information. That's PMI, and it has to do with probability and entropy and so on. But let's not dwell on that. What I'd like to do now is go to the notes. So every one of these lectures has slides and notes that go along with it, and they're very useful. If I can get this working, there we go. Yeah, so this is the slides that go with this lecture. These are the notes, and there's a links, as Srinivas showed us, there's links off of the course page that you can find all this stuff. So let me just quickly, oh, I'm not sharing my screen, hold on. Let me share the right screen now. Let's see, there we go. You're now seeing the notes, right?
Yes.
Yeah,
Yes.
Thank you. Yeah, but now I'm gonna take the sharing away for a second and go back to the other screen because I wanna show you the course page where you find all this stuff. Let's see, share the course page. The main course, not that one, not that one. Okay, not that one. Not that one. Sorry. Here we go. Yeah, that's where I was. So share this one. Go back to the main course page. And okay, so here's the course page for the 2019 course that we start with. There's a lot in this page, but you scroll way down to the past, to the coursework, and even past that, and then they have the schedule. And so here's where you find the slides. For each lecture, you can find slides, you can find the video, and you can find the more detailed notes that come with it. And you can also find the code, that's related to whatever homework assignment is being discussed there. So you can see that some lectures don't have homework assignments, but this is where you find all the stuff you need for the course. So you should really familiarize yourself with this homepage because it has all the resources that you're going to need for the class. Okay, stop sharing this. Go back to the course notes. Notes. There we go. Back to the course notes. Okay, so this is like a 15 or 13 pages of. There's not a lot of you get through a little bit of this math, and the rest of it's just a discussion of. He's basically okay. This guy Manning is the guy who, with his graduate student, invented the glove embedding technique, and so he's giving us an introduction to what glove does and how it's built and so on. And then he talks again about the analogy problem, and here it is again as the vector as a problem in vector space. It's basically a maximization problem. You just find the vector that makes these vectors have the proper relationship if they're analogies. So anyway, we don't need to go through this in detail. What I would like to do, though, is go through his slides. Where were they? Did I just lose them? Probably just lost them. Yes, I did. I closed them by mistake. Sorry, I'm going to have to open them again. Let's see. Open. Project handout, instructions, lecture 2. That's the one I want. Yeah. Okay, so let's go through this. These are the slides that he went through in the video, and this is what we really need to get through. So he organizes it very well as usual. Optimization basics, counting words, the GLOVE model that, again, he invented, evaluating word vectors, and then using for word senses. This is like, you know, like a recommendation or something, or like you ask whether a movie review is positive or negative. That's what they mean by word sense. And then another bit about the course. So let's try to get through all of this stuff. All right, so reviewing the main idea of word2vec, you have a center word at some position, and then you consider a context window that can be a variable size, extending in both directions from the center word. And then you want the probability of an okay, O is for outside. That means the word is in the context window. That doesn't include the word itself. The probability of a word occurring in the context given a center word is given by this softmax function. Now we've seen that. U is the outside. Again, there's two different formulations for a word vector. There's a U if it's an outside word, if it's part of the context, and V if it's in the center. Let's see. So U, V. Okay, so U dot V is a dot product. U dot V transpose, because remember U is a row vector in this case, right? And V transpose, V is also a row vector. So in order to get the dot product, you have to take a transpose. And then the softmax gives you the probabilities.
Hey, Joseph, a point that he raised in the video, which I think is just like a subtle thing that might be really important to folks, is that usually when we do this mathematically, we think of them as column vectors, but the reason why he's using them as row vectors is because that's how TensorFlow and PyTorch represent them. Yeah,
that's a really good point. And when you go through Jeremy's mathematics, I've noticed this in Jeremy's lectures, that you know, I'm used to thinking of everything as a column vector, and then a matrix operation on a matrix operates on a column vector from the left. A matrix is on the left and the column vector is on the right, and then you do the matrix multiplication. But Jeremy thinks about it backwards, and that's because PyTorch and TensorFlow think about it backwards. They think about the vector as a flat vector, a horizontal vector, and that vector is multiplying the transpose of the matrix. And you get the same result, of course, but it's just a different way of thinking about it. It's a completely equivalent representation. But it took me a while to, you know, some of these lectures that Jeremy has, and he just quickly sketches out these matrix operations, and it didn't make any sense to me until I realized that he's basically using the fact that, you know, a matrix, let's say a matrix A times a vector X is the same thing as the transpose of the matrix of the vector X times the transpose of the matrix A. They're the same thing. And PyTorch and TensorFlow think in this transpose space. So that's a really good point, Larry. I'm glad you brought it up. All right, continuing. So word2vec maximizes the objective function by putting similar words nearby in space, just like the other method that just like the counting method that we talked about before. You know, in this embedding space, words that mean the same are going to be close by to each other. So that's the end result. Okay, optimization is done by gradient descent. We've all been introduced to that. The idea is if you have a function and you find, in order to find its minimum, you just go in the negative direction of, you just take steps in the negative direction of the gradient, or in the direction of the negative gradient, and then you'll get there. And the idea is that, you know, the step size is a parameter, it's a hyperparameter, and it can be adjusted according to some schedule. It doesn't have to be the same step every time. So an adaptive method would make the learning rate smaller, the step size smaller as you get closer to the minimum, as the slope gets shallower. Yeah.
Same as the learning rate.
Yes, sir.
Is the step size the same as learning rate?
Sorry, I have to turn up my volume because I have a lot of background noise and I couldn't hear you. Could you repeat your comment or question?
I was saying if the step size is the same as the learning rate that we refer to in FastAI.
The step size is, I didn't get the last part.
Learning rate?
Yes.
Is it the same?
The step size is the learning rate times the gradient. Is that what you were trying to say?
I see. Okay. No, I was just clarifying. Yeah, thank you.
Yeah, exactly. I mean, the step you take is given by is always in the direction of the negative gradient, but the multiplier, which is the learning rate, that is a hyperparameter that can be learned or that can be set in advance. Okay, so that's just a basic review of the gradient descent method, and here it is again. You know, you have a vector and you want to change that vector. You want to update that vector by subtracting from it the step size times the negative gradient, or adding to it the step size times the negative gradient of the loss function with respect to that parameter. So that's how you would update each parameter. So this is the update in matrix notation, where theta would be a column vector of weights. Theta old is a column vector. The gradient of the loss function with respect to the thetas, that is as a matrix. If you're interested in this bit of mathematics, or if you're not familiar with it, do come to the review of Jeremy's paper, that little mini review that I'm having, because that's going to go into all the details of this differentiation process. So then this tells you the update equation for a single parameter, and this is the algorithm. You just keep updating until you get so close that it doesn't change too much, that that your loss function doesn't change anymore.
Hey, so Joseph, I don't think that's right though, right? It says the step size or learning rate. I don't think that's, I think the step size is actually that entire bit on the right.
That's correct. In my mind, that's right. The learning rate is a multiplier, and together the product makes the
learning rate's the alpha, right?
Yes,
yeah.
yes, I agree with you. Yeah, you're right. Okay, so stochastic gradient descent. Right, so then they say the problem is that if you to do gradient descent, you actually have to compute the entire, you have to compute your updates for the entire column of weights and for the entire set of inputs, and that can take a long time. So instead, you can make updates for each example in your data set, and that's called stochastic gradient descent. You can update each sample individually, or you can update a batch of samples at the same time, a small batch of, say, 32 or 64 or 128. And when you do that, the updates are going to be much noisier, but if you keep, but the average from all the batches is still going to get you to a good solution. So an individual update, if you update your model based on a single sample, you can imagine that that's going to be a very noisy update. But that's okay, because if you do it for all the samples and then you average together the update, then you're going to get, and then you continue to update serially for each sample, then you're going to eventually get to a good one. Okay, so now he talks about doing it with word vectors, and it's a sparse. The idea is that in these context windows, the context windows have only a few words in them, so this matrix is going to be very sparse, right? It's not, most of the words in the, remember it's an n by n matrix, and most of the entries are going to be zeros. There's only going to be a few words that are in context of a given word, that occur in the context of a given word. So talks about matrix operation. There's two variants of the word-to-vec method: the skipgrams method, where you start with the center word and you try to predict the context words. And the second way is called continuous bag of words, or SIBO. And here you start with the center word and you try to predict you start with the context words, a given set of context words, and you try to predict that center word, the word that belongs in the middle. So those are just two different ways of seeing the same thing. but they do have differences, and it turns out that the skipgrams method is much better in performance. Now they talk about additional getting better training by using negative sampling, and I guess, let's see. So far we talked about naive softmax, but there's this technique called negative sampling where instead of sampling, so if you go back to this expression of the softmax, it's very difficult to compute this because you have to compute the denominator here, which requires the entire data set. So the idea of negative sampling is that you pick at random a bunch of words and you tell it that these words are not going to be context words, and then you train it based on that idea. And the reason, again, is that the normalization factor here is much too computationally expensive. So they implement the skipgram model. So word2vec is basically, to describe it, it's the skipgram model. That is, it's predicting the context words given the center word. That's the skipgram model. And it's doing that with negative sampling. And the negative sampling is you add a bunch of noise pairs, that is the center word paired with a random word, which is much less likely to be a context word. So you just assume that when you pair the center word with a random word, that its likelihood of being a context word is 0, even though every once in a while that might not be true, but on the whole it works out. Okay, skipgram model with negative sampling. The sigmoid function is the objective function that they use. J of theta is over the entire corpus, and so T is all the words in the corpus, and so you're summing. So JT of theta is the loss function for a single word, and then you're summing over the entire corpus and averaging to get the loss function for the whole corpus. So let's look again. Let's take apart this little piece here. The loss function for a single word. That is going to be the log of. It's going to be the logarithm of the sigmoid function. Now, the sigmoid function maps it's the log of the sigmoid function of the dot product of the outside word vector times the context word vector, the dot product of those two vectors. So what is the sigmoid function? The sigmoid function maps a number. That's what the dot product is. It's just a number. It maps a number to something between 0 and 1. So it squishes all the numbers to a number between 0 and 1. So these vector dot products can be any number from, they can have numbers from negative infinity to infinity, these dot products, in the embedding space. But the sigmoid function squeezes them to between 0 and 1. And then the logarithm function, somehow they always end up taking, the loss function is always the logarithm of something, and it turns out to be make things mathematically easier. The idea is that if you're trying to minimize something, it's the same mathematical problem as minimizing the log of that something. If you're trying to minimize a function, since the function the log of the function tracks the function. The function increases, the log of the function increases. So minimizing a function is the same as minimizing the log of a function. So there's no problem with doing that. It turns out to be an advantage to minimize the log of a function. So that's what they do. Okay, why are they doing this? The expectation value of the log of the minus. So what they're really doing is the log, they're taking the log of this thing, okay? And the log of this probability is the log of the numerator minus the log of the denominator. Or actually, let's see, it's the sigmoid of. So let's see, somehow they're transforming this in a way. They're taking the sigmoid of the numerator, or this is the sigmoid of that thing. Okay, so yeah, so this is the sigmoid function of the numerator, and the denominator is basically a normalization. And that's what's going on here. The normalization is the same as the expectation value of the log of the negative vector, the negative dot product. So let's see. This is the definition. This is the definition of the sigmoid function here. Question.
Sorry, I've never come across the word negative sampling before. What? Any idea what that is?
Yeah, the negative sampling is when you introduce word context. Okay, remember we're talking about pairs of center word and outside word, right? Center word and context word. So you introduce some negative samples. That means you introduce some center word paired with random word instead of center word paired with one of its real context words. Does that make sense? So given a word in a dictionary, there will be a set of context words, words that occur sometimes within a context window of plus or minus whatever of this thing, right? So those are the positive samples. But now they're saying, let's throw in a bunch of negative samples as well. And a negative sample is a center word paired with a random word. And the idea is that you say that never occurs in context. And so its dot product is going to be 0. And so you just throw these negative samples in with the mix, and that helps the model to converge. That's that idea.
The explanation of negative sampling is covered in the first set of notes for the first lecture. And the other point is basically through negative sampling, they're trying to approximate the softmax, which is to say increase the probability of co-occurring words and reduce or make 0 the probability of the words that do not co-occur, which are the negatively sampled words. And negative sampling basically says take a bunch of samples which you do not think will occur and reduce that probability and increase the probability of words that you think co-occur.
Yeah, that's what the sigmoid function does, right? It for words that have low probability, it makes it even worse, it makes it even lower. And for words that have high probability, it tends to amplify that probability.
And I think what I liked the way that he was putting is that we are training a logistic regression, a classifier that learns the differentiation between words in context and words out of context. So
that's
the
a
negative,
good point.
yeah.
That's a good point. Okay, great. And okay, so someone mentioned in the notes in the group chat that there's a good explanation of word2vec with visualization with negative sampling. I almost read that before this meeting, but I didn't get to it. It's Jay Alamar's. And so look on the group chat. And Wen Chang, if you would mind, please post that. If anybody actually who's posting links on this chat, please post it to our Slack group, and that way it will survive after our meeting is over. Does that make sense? For all the people that are posting these useful links, please post them on the Slack group as well.
Sure, I'll do that.
Thank you so much for that. Yeah. Okay, so where are we? So this is the definition of the sigmoid function, and this is our overall loss function that in this case is to be maximized. Where is this? Okay, so let's keep going. So here's they talk about the negative sample, outside word, context word, U. I'm not sure what this U is. We take negative samples using word probability, maximize the probability that real outside word appears, minimize the probability that random words appear. So we're actually training. We're saying that in some way we're saying that context words are somehow in a positive class, because those are the words that are really in context. And these random words that we choose, the words that we choose at random to pair with the center word, we say that those have 0 probability of being in context. So we're actually having 2 classes, a positive class and a negative class, as Marat pointed out, right? And let's see, then he's got this trick that they use where instead of using, let's see, I'm not sure what this capital U is. Does somebody remember what that is? I didn't see that defined here. It's probably in the notes.
I think that's the set of vectors in the corpus.
Okay, okay.
It's basically the matrix Joseph, of outside words, and then and I might have this reverse, but one is the set of outside words and set of contact words, but the matrices.
Right. Okay. Thank you. So basically he's saying, let's not just take the straight probability, but instead let's take the probability to the power of 3/4. So you take this whole U matrix, and I think that it should be the whole U matrix is taken to the power of 3/4. You know, so that means you take the cube of the matrix and then you take the 4th root of it. And they just find empirically that this works. They didn't give a derivation of it. It just works better than using the straight probabilities, okay? And the idea is that it says that it makes the less frequent words be sampled more often, so that, because you don't want, like, in any vocabulary, there are certain words that occur very, very frequently, and they could and the words that occur less frequently might be more important. And so this, by taking the 3/4 power, it makes those words more important in the model. Someone had a question or a comment?
No, again, they give a mathematical example in the notes of how it doesn't impact the most common words much, but it significantly increases the probability of less frequent words. And it increases the example. In the example they give, it increases it by about 3x, whereas the very frequent words changes very less. So
yes, so that's what it does. It as Sternbach said, it makes the less important words stand out. The less frequent words stand out. The more frequent words, it reduces their impact on the model. Okay, so let's see, co-occurrence matrix. So a co-occurrence matrix, we've talked about that. That is this this n by n matrix, which has the counts of the words, the context words that occur around each center word. Let's see, why not capture co-occurrence counts directly? Yeah, and there are techniques that do that. Word2Vec is a complicated model. I think it uses I think it uses neural nets. But latent semantic analysis is a technique to accomplish a similar task, but it's not based on deep learning. It's basically just, you start with the word document co-occurrence matrix, and you apply some normalization weights. I don't know if you remember TF-IDF that we had in the FastAI's class. You normalize the counts by this TF-IDF. It does the same thing as this power of 3/4 thing. It emphasizes the rare words and de-emphasizes the frequent words. And then you apply SVD, singular value decomposition, to factorize this matrix, and then you get the embeddings directly. And then from those, you also define the metric on that space to be the same cosine distance that we've already talked about. So this is a way to get the co-occurrence counts directly. That's the what they call LSA or LSI, latent semantic analysis. Okay, so let's, I see that I'm not going fast enough here, because I want to make sure we're done by 9:30 so we can proceed with the next meeting. So this is what these co-occurrence matrices look like. We've seen that already. Problems are that they increase in size with vocabulary. They're very high dimensional, require a lot of storage. The classification models that you come up with can have issues, so they're less robust. So Word2Vec, the idea is that the main idea from this lecture is that Word2Vec and GloVe are the ones that are the methods of embedding that perform the best. Dimensionality reduction, we've seen this. It's in the homework. SVD, simple SVD. So this is how to derive word vectors just by simple SVD. And it turns out not to work that well, even though it's straightforward mathematically. So here is an example. You do this on a very small dictionary, and it's not, I don't see very much meaning there. So, but that's what happens when you do it on a very small vocabulary. Hacks to X, scaling the counts. I think we need to go through all that. Interesting syntactic patterns. You'll see in these notes that he often uses words like semantic and syntactic, syntax and semantics. So you should get those two words straight in your mind. And what I always remember is that semantic has to do with meaning. Semantics has to do with the meaning of a word, whereas the syntax has more to do with the structure of the language. Like, so it has more to do with grammar. So for example, a semantic relationship would be to find a synonym, to find a word that means the same as intelligent, smart, apt, that kind of thing. A synonym. That's semantics. Or find an antonym. That's also involving semantics. But when you have relationships like big, bigger, biggest, those are syntactic relationships, because every language has a structure for that. Big, bigger, biggest, small, smaller, smallest, good, better, best. These they relate to the structure. They relate back to the structure of the language, and they're more related with syntax. Okay, so now he's talking about semantic similarity. that must mean meaning-based similarity. And so here he has speak, speaking, and spoke. These words cluster in the embedding space. Take, taken, taking, took. These all cluster. So that's what they mean by syntactic patterns emerging. Sorry, I got it wrong. So this is the structure of the language. Syntactic relates back to root words, right? This is why these words are clustered, because they all have the same root. So this is syntax relating to the structure of the language, whereas semantic patterns have to do with meaning. So here we have driver, drive, driver, swim, swimmer. They seem to have this directional relationship, right? Learn, teacher, learn, teach, bride, marry. They have this directional relationship. Janitor, clean. So these are the semantic patterns, and these have to do with directionality. This is the thing that Murat pointed out early in the class today. Okay, so we're talking about comparing these two methods of getting word vectors: count-based versus direct prediction. The count-based are well, I'm not sure which. The count-based are these methods: latent semantic analysis. HAL is another method. Coles is another one. But the point is that they go directly. They get the embedding vectors directly from factoring the matrices using SVD or something. So those are methods. They don't go into a lot of detail, but you can look these up and just really quickly get yourself familiar with what they are. You don't have to look all of them up, but look up a few of them, like LSA and HAL. Get an idea of what they are. They just allow you to directly compute word embeddings, whereas these are more indirect. They're based on prediction. Skipgram and SIBO with word2vec. And then these are other models that I suppose they'll be talking about later in the class. The advantages of these models are that they scale well with corpus size. They get better and better with larger and larger corpus. But a problem, he says, is they make inefficient usage of statistics. I'm not sure why he says that. They generate improved performance on other tasks like analogies and like other things like, let's say, named entity recognition. These are common tasks that they do in NLP. They do well on these tasks. They can capture complex patterns beyond word similarity. Now this is like a segue into his work with Glove. His graduate student Pennington and Socher may have been a postdoc or whatever, and Manning, they invented this technique called Glove. And their critical insight was ratios of co-occurrence probabilities and code meaning components. So let's just take a look at this really quickly. The conditional probability of a word, given that its context word is ice, it could be if X is a solid, if X is the word solid, then these two do relate, and so you'd say that condition probability is regularly that conditional probability is sort of loosely you could say it's large, because ice and solid are related. But on the other hand, if the word X was gas, the probability of gas, of gas being the center word, given that ice is a context word, that should be small. I'm not sure if I'm getting this order correct, if this is the center word and this is the context word, or if it's vice versa. It doesn't matter in this case anyway. If X is the word water and ice, those words do occur those do occur near each other, so that's large. So this is basically just qualitative probabilities. But then if you take a look at these, the ratio of this to this is going to be large, because large over small, a large number over a small number is large. A small number over a large number is small. A large number over a large number is sort of indeterminate, but they're about equal, so they could be about 1. A small number over a small number could also be about 1, but you could get in trouble thinking that. But anyway, that's sort of loosely what their main finding was in this paper. Let's see. Now they're putting in some real numbers for the same, some real numbers that they got out of their modeling, and these are the actual ratios that they got. Let me see. I want to manage participants. I hear some background noise, so I'm gonna see if I can find the source of that. Let's see. Nope, I don't know where that's coming from. Okay, anyway, back to this. So here's the real numbers, and that's the numbers they get. Encoding meaning. When they talk about bilinear model, they mean that the context window is both in front of and behind the word. That's what they mean by a bilinear model. W-I-W-P-I X dot W-A minus B. That's the log of, let's see, ratios of co-occurrences at probabilities. So linear meaning components. So the W's are the words, and the dot products are, I'm not sure what to make of this expression here, but certainly if W, yeah.
I think it was about, because he was taking probability ratios, and by taking the log, now you have just subtraction of the vector. So
yeah, I mean, that's how, yeah, so that's how this would work. If the probability itself is, well, if the log probability, well, I don't understand how this follows from this, actually. Generally, if you take the log of a ratio, that's the log of the numerator minus the log of the denominator. So I'm not sure how this relates to this. If the log is bilinear, then
I think he was assuming that for the.
No, I see it. It does work because log of, okay. So if you take this expression, if you set the log equal to this product, then when you take the log of pxa, you get log of p plus log of log of px, or log of wx plus log of wa, and on the bottom it's log of p.
Yeah,
minus.
Yeah,
it doesn't work.
Well, it looks like it's a distributive property. That's what it looks like.
It doesn't work though. Yeah, but it doesn't work because if you work this out, the log of the numerator is a difference. Oh yeah, it does work. It does work. If you take this, let me write it out. And then I'll show you.
Yeah, so the numerator will be Wx into Wa. Denominator is Wx, Wb. You take Wx common and you get Wa minus Wb.
Yeah, let's write that out.
You have combined two terms.
Yeah, let's write that out. Hold on for a sec. Let's see. I need to find my pen if I can get it again. There. There we go. Okay, so if we take, let's just write this out. The numerator, p of x given a, is going to be, okay, so here's how they set it up, that the log of x given a is the product. So it's going to be wx times wa. and then the log, that's an x, and then the log of p of x given b is just going to be wx. This should be a times dot, okay. Okay, so now if you take the log of this thing, that's just going to be the difference, log of p of xa minus log of p of xb. So if you take, if you then, does everybody see that? The log of, you know, the log of x over y is the log of x minus the log of y, basic property of logarithms. So the log of a ratio is just the difference in the logs of the, you know, the difference in the log of the numerator and the log of the denominator. So, but we've already calculated the log of the numerator and we've already calculated the log of the denominator. So we basically have the numerator minus the denominator is wx wx times wa minus wx times wb. And as people pointed out, this is the this is basically just the distributive property. You can factor out the wx and you get this, right? Wx occurs in both terms, so it's just wx times wa minus wb. So that's that one. Let's see, where am I in terms of time? I've got 10 more minutes and I have to clear all the drawings, and let's just get my mouse back. All right, keep going. Okay, so this, so he says that an advantage of his technique is that it's fast, it's scalable to huge corpora, and it performs well with even a small corpus and a small dimensions. So, and he goes into a lot more detail in the notes, which I want to get into. Okay, so this is some glove results. If you find the nearest words, you get all of this, which seems like it works. So then he talks about ways of evaluating word vectors. You can evaluate them on intrinsic or extrinsic tasks. And intrinsic is basically some kind of a specific intermediate task that can be done quickly, just to give you like a scoring so you can understand whether your thing is performing well or not. But you always have to connect it to a real task. And that's why the NLP folks have all of these benchmarks, and there's new, you know, there are new ones being created every day, but there's all these benchmarks for different tasks like named entity recognition, sentence sentence, let's see, what else? Question answering is another task. There are a lot of main tasks in NLP beyond just looking for synonyms, beyond just looking for the next word in a language model. So they have benchmarks for all these different kind of things, and that's what they mean by the extrinsic measures, which are evaluation of your word embeddings on a real task, and when you get to a real task, it takes a longer time, and so on. So this is that man-woman task that we talked about. The intrinsic word vector evaluation is based on analogies, you know, and you just solve for these. You just solve for the the analog vectors using this equation that we talked about a little bit directly in the embedding space. And then Glove comes up with an interesting, you know, it works well. It has, you know, the relationship between sir and madam is a direction. There's these directional relationships between these words that involve the genders, right? Sir is the male version, madam is the female version, heir is the male version, heiress is the female version, king, queen. So the male versions are along the bottom, and the female versions are along the top. So it's showing that Glove works well there. And here's another dimension where you talk about company names and their CEO names. This is named entity recognition, right? The company name is an entity and the CEO is another named entity. And here the relationship is horizontal. The companies are on the left and the CEOs are on the right. And they're not just on the right, but they're almost parallel. In other words, they're in the plus X direction. If you want the CEO of Caterpillar, you go looking in this direction and you'll find him. If you want the CEO of Walmart, you go looking in this direction and you'll find it. So him or her. So that's how that works. Superlatives. So this is, these are semantic things, the meaning, they're meanings, right? But these are the superlatives, slow, slower, slowest. Those are syntactic relationships. They relate to the structure of the language. Okay, so he talks a little bit about this, intrinsic word evaluation, analogy evaluation, hyperparameters. So here he doesn't really explain all these different models, but the main thing to notice is that these are all different models for constructing word embeddings. I suppose if you were really interested, you could go look them up online. GloVe is the one we're talking about, the one that he's interested in, because he's shown that GloVe gets the superior scores in almost every one of these tasks, right? If you look at where the best scores are, they're underlined. And here is the dimensionality of the word vectors and the size of the corpus. And those are the sort of the hyperparameters. And he's doing some kind of a semantic testing and some kind of a syntactic testing, which he hasn't really specified what these tests are, but you can imagine they're similar to the ones that we saw up here. And then he has scores, and he shows that in all of these, almost all of them, GloVe gets the best score. And there are only two models that we really know about, and that's SIBO, that's the Word2Vec, and GloVe, that's the one he's talking about. And then I guess we also understand a little bit about SVD. So there's other methods which you could look up, but the point of this drawing, of this graph, is that is that GloVe does really well on these tests. Analogy evaluation and hyperparameter. This is interesting because I know that some of you had asked the question in our last meeting. You said, like, how do they determine the size of the embedding vector space, and how do they determine the size of the window? Because that's kind of a mystery, right? Well, those turn out to be hyperparameters that can be, and he's explored those hyperparameters in this GloVe paper, and they actually found that empirically that good dimension for an embedding space is about 300, and a good window size for this GloVe model is about 8. So that answers the question of how they get these things. They don't just pull them out of a hat. They actually do simulations, and they determine them empirically. This is with respect to a paper that they put, but one of the that he put as a link, and these two people wrote this paper. And the interesting thing is that using a higher embedding dimension doesn't lead to better performance. You quickly ramp up to a peak somewhere around 300, and then if you increase the dimensionality of the embedding space, you don't get better performance, and that's kind of surprising. So, these are stating some results of that test. And then here's another graph that stands out on analogy evaluation. They showed that GloVe is way superior to this Word2Vec skipgram method that we introduced in the first lecture. The accuracy here is like 70% or under 70%, whereas that is for the Word2Vec method. But for GloVe, they're getting like over. This is kind of a misleading graph because it's not between 0 and 100, it's between 60 and 72. So, here we have 68, 69% performance for skipgram, and GloVe gets better. It gets around 71% or something like that. So it is somewhat better, but not as much better as this graph seems to show. If you just look at it quickly, you might think, oh, that's like 20% better, but it's not. So it's only a few percent better. Okay. The other thing is that more data helps. Wikipedia is better than news text. They talk about the number of tokens in the training set. 1 billion, 1.6 billion, 4.3 billion, 6 billion, 42 billion. And notice that on semantic tests, there's not that much, you don't see much of a trend with corpus size. Even a relatively small corpus of 1 billion gets a score near 80. Where you do see it is the syntactic, that is with structure, with the language structure, like things like root words and things like, connecting root words, being able to find all the root words and group them in a cluster, or being able to show the directionality between slow, slower, and slowest. These are the syntactic tasks. Those definitely show a trend, getting better and better and better with the size of the corpus. And the other thing that's notable is that for some reason, it's easier to get higher scores on these semantic tests than it is to get high scores on the syntactic tests. Right. And I'm not sure why that is.
Hey, Joseph, may I ask a quick question, please? Was there any mention about removing stop words from these corpuses? Because it looks like they don't do that at all.
They don't do that anymore, because now with the compute power that we have, you don't have to. You know, in the old days, stop words were so numerous, and that you could really significantly decrease the compute required for your modeling by removing all the stop words. But now they find that you don't need to, because you have so much compute power, and it helps to keep them in. It actually gives you a little bit of an advantage to keep them in. Okay, so yeah, thank you. Yeah, so these are just, again, comparing tests, and he makes references to another paper. And this is kind of really interesting. I've got 1 minute left here. Polysemy is the idea that one word can mean many things, and they've had some success in untangling the meanings by basically just adding up the word vectors, adding up some weighted combination of the word vectors for the different meaning clusters, and then coming up with a single word vector. And you might think, well, how can you then pull things apart after you've lumped it all together in one vector? But it turns out that if you do it in a smart way, using sparse coding, you can pull it back apart. And as a very simple example, you can imagine that if you take a vector with 3 elements, and the elements can only be zeros and ones, right? And if you add, and you have 3 different meanings, you know, one meaning is zeros is denoted by 001, another meaning is 010, and another meaning is 100. You add those 3 all up, you get a vector 111, and yes, you can pull it back apart, because the way you've constructed it means that you can pull that apart into its basis vectors, and those will be the individual meaning clusters for those words. So that's how that can work. Anyway, we are out of time. I didn't quite get, but this is the last word here. The thing that everybody should remember here, this is difficult when you find yourself struggling reading through these notes, and when you find yourself struggling listening to the videos. This is a hard advanced graduate class at one of the premier institutions in the world for NLP. This guy, Manning, has invented a lot of the structure and a lot of the stuff that people use in NLP. So let's all remember that, and don't beat yourself up if you're having a hard time. Just realize, you know, we don't have TAs, but we do have each other. So if you have questions, you can write to the Slack channel and ask them, and hopefully we'll try to answer them. Anyway, I've gone over. I'm going to quit now, and I'll thank you all for being here. See you next time. I'm going to let you go so you can go to Darren's meeting.